arc measures. We're going to start with arc measures, and then we're going to look at the chords. Let's see what we got here. Okay, well, first of all, let's talk about what an arc is. So an arc is like this little piece of a circle. That's an arc. It's a little piece of a circle. So we're going to be talking about that a little bit. So a central angle, we need to know what that is in our study of arcs. A central angle is an angle whose vertex is at the center. And so you can just look here, the radii are kind of making up the rest of the angle here. So this angle ACB is called a central angle, and you know, we have lots of different central angles, but they're all centered around the center of the circle there. What else we got here? A minor arc. What's a minor arc? It's part of a circle. Now let's think about what's the whole circle all the way around? How many degrees? 360. So a minor arc is an arc that is less than 180. So it's an arc that's less than halfway around. That's a minor arc. A major arc is one that's bigger. So it's between 180. So you go more than halfway around to almost the end there. So that's a major arc. And the semicircle would be exactly half the circle. Okay? And so these are formed by different radii. So if you have a diameter, that's going to form this semicircle. So, you know, those are little bits and pieces for that. Fun facts. Ready for some fun facts? It's all fun facts. A minor arc, we name them by their endpoints. And this little thing here, that signifies that we're talking about an arc. So this is minor arc AB. We just talk about their endpoints. A major arc and semicircles are named by the endpoints, but also at points in between them on the arc. So ABB, let me bring up the picture here. So if this is a circle, circle C, the minor arc is AB. But the major arc is ABB, going all the way around. Let's see. And the way we write the measure of an arc is we use M, just like measure of an angle, so measure of an arc AB. And we're talking about its degree measure, we're not talking about its length. So we're going to be talking a little bit later in the next few classes about what the length of this is, but we can also classify it by its measure, and it is a degree measure, 360 all the way around, 180 halfway around, and then fractions of that in between. Now the degree measure is the same as the central angle measure. So this angle, ACB, is a central angle, and it makes this arc right here, AB. If this central angle measure is 50 degrees, then the measure of the arc is also 50 degrees. It matches the central angle. Make sense? Yeah. Okay. The measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. This is like the segment addition postulate, only I guess it's an arc addition. I don't know why we don't have a formal postulate. But it's the same thing. So if you add BA, add arc BA to arc AC, you will get arc BAC. Yeah, so that works the same. So, okay, let's look at this one again. Here's my minor arc. Let's say it's 50 degrees. If I want to find the major arc, ABB, how would I find its measure? Jerry, how would I find its measure? Right. The whole thing's 360, so if I subtract out the 50, so this major arc would be 310 degrees. The whole thing's 360. Yeah. Okay, congruence. What about it? Circles are congruent if they have the same radius measure. That's how you tell if circles are congruent. Which makes sense when you think about the definition of a circle. All the points that are equidistant from this particular middle, that means the radius would be the same for these congruent circles. Arcs are congruent, not only if they have the same measure, they do have to have the same measure, but they also have to be congruent circles. So same measure and same radius measure. So, for example, are these congruent arcs? Well, yeah, they all open up 145 degrees, so that's good. But the other reason that we can say they're congruent is because these radii are congruent, and I know that by the congruence mark. Are these congruent arcs? Well, they both open 120 degrees, that's the central angle, and that would be their measures. However, this circle is not congruent to that circle because it's got a radius of 5. This one has a radius of 4. Not congruent. Yeah? That makes sense. Doesn't it? Yes. Okay. So looking at a couple of examples here, where the middle of the page, hopefully you can find it there. Find the measures of each arc of circle P, where RT is the diameter. So this is the diameter, here's the center. Now whenever I do these, the first thing I do is mark my diagram. So if this is a diameter, and diameters make semicircles, well, what's this entire angle going to be? 180. So if this piece is 110, what's this piece? And then this whole thing here, 180. I find that if you do this first, when they start asking you what the different measures are, it's a lot easier. So if we want arc RS, so RS, and then that's going to be the minor arc, RS. Because you can do RS this way, right? But if they just say RS with 2 letters, they're talking about the minor arc. So what's its measure? 110 degrees. It matches the central angle. What about RTS? Now that's the major one. So going around this way. RTS, what would that measure be? Jerry? 250 degrees. How'd you get it? Right. So one way to do that is say, well, if this piece is 110, the missing bit is going to be 360, the whole thing minus 110. And that's where the 250 is coming from. The other way you could do it is, see how I've marked my diagram? You can add up these measures. Well, if this one's 180, that makes that arc 180. This central angle is 70, that makes that arc 70 degrees. 180 plus 70, 250. Either way is correct. RST, what's the measure of RST? That arc, go ahead. 180 degrees. And you can see that it's formed by a diameter. So this arc will be 180 degrees. And then ST, well, I can see its central angle is 70. So it is also going to be 70 degrees. So it's really, I think, easier if you kind of mark up as much as you can before you start to kind of figure out what these different measures are. So, questions? Because we're already on the U-tries. There are a couple of parts to the U-tries. This is kind of like what we just did, find these arc measures. This one you're doing 2 things on number 2. First, decide if it's major, minor, or semicircle, and then find its measure. And then the third thing you're going to be doing is telling whether highlighted arcs are congruent. And I think it actually showed up on the paper pretty well. So just take a couple of minutes and I'll do these things and we'll talk about it. Pretty good. I'm just going to start putting answers up so people are just about that. Keep working if you're still working. If you are done, take a look up here, see how you did. And if you have questions, let me know. I'll page over in a minute. Minor 70 degrees, minor 60, semicircle 180, major 310, major 290, minor 3. If you got through parts 1 and 2, are there questions? My advice would be to find this first, right? Here's 180, so this whole thing is 180. That's 70, that's 50, that's 120, right? And that means this one has to be 60. And then hopefully once you find all those pieces, it's not too bad to do it. Let me put up the answers for part 3. This one we're looking for congruent arcs. And basically what I'm looking for are the radii congruent and are the arc openings the same. That's what I'm looking for. I think in all cases they may be arc openings the same. So you're basically looking for the radii. How are we doing? No, yes, yes, no, yes. Good? Questions? Yes, sir. The reason it's not, now they're both open 180, it's just look at the radii length. This one, this radius length is from here to here, from the center to point Y, and this radius length is from the center to point Z. So the circles aren't congruent. Circles have to be congruent for them, the arcs to be congruent. Now this one is kind of playing a little thing here, but it really is the same radius in both. So you can see that the radii are congruent. So they can make the picture a little complicated. Other questions on that? All right, let's look at chords. We're on the back now. Chords, just to review what a chord is, it's a segment with endpoints on a circle, and you get 2 arcs. So here is my chord AB, so I have a minor arc here, and I have a major arc on the other side. If one of my chords is a diameter, then I get 2 semicircles when I look at the 2 chords that are formed, 2 arcs. So these are some of the theorems. Now we looked at this a bit. I had you kind of do this drawing already. So hopefully you've got your drawings, you can look at them at the same time. Let's talk about them a little bit though. So in the same or congruent circles, so as long as your circles are congruent, all these theorems are true as well. 2 minor arcs are congruent if and only if, by conditional, their corresponding chords are congruent. So here's 2 chords that are congruent. That means that arc AB and arc CD will be congruent. Conversely, if arc AB and arc CD are congruent, then you can conclude that the chords AB and CD are congruent as well. So it's an if and only if either way. These next 2 theorems are kind of similar. If one chord in a circle is a perpendicular bisector. So we should probably show that these two pieces are congruent. We should probably do that in your picture as well. Oh, good. Right? Perpendicular bisector. If that's true, then it must be that this chord was a diameter, because that's the only way you can get there. So if you have a situation, two chords are bisecting, and one of them is a perpendicular bisector, the other one has to be a diameter. This is kind of the converse. If a diameter of a circle is perpendicular to a chord, so if that's true, a diameter is perpendicular to a chord, then it must be a bisector as well. So it's a little add-on to that one. Okay, so that's why those two pictures kind of look the same. The last theorem that we're looking at is in the same circle again, or congruent circles. So again, if you have congruent circles, all this works as well. Two chords are congruent if and only if, by conditional, they are equidistant from the center, same distance from the center. Now, when you measure distances from a center, what distance do we mean? You're getting there this way, that way, what's the distance from point E to this chord? And it's always going to be that perpendicular. Dropping a perpendicular is how we measure distance from a point to a line. And we saw that a little bit with constructions as well. So that's why we see these little right angle markers. That means distance from E to that chord and E to that chord. So what does this actually say? Okay, two chords are congruent. This one is congruent to that one, if and only if they are equidistant. So this distance from here to here is the same. Conversely, if you have the situation where the distances are the same from the center to two chords, then it must be that the chords are congruent. So again, I think the pictures are more helpful. If you have this situation, AB will be congruent to CD, and if AB is congruent to CD, then EF will be congruent to GE. Yes, sir? They are, I think they're slightly different. More or less. Let's look at some examples here. So this is on your paper there, middle of page 2. Given circle D. So if the measure of arc AB is 110 degrees, find the measure of BC. Now, why? Tell me why, Christian. You're going to give me the answer you're going to give me. Yes, because the chords are congruent, that means the arcs are congruent. So the measure of arc BC will match the measure of arc AB because these chords are congruent. And then the second part, so it's not related to the first part, so now this no longer exists. But the same picture, if the measure of arc AC is 150 degrees, find the measure of arc AB. Again, I don't want the answer. I'm like, how do you figure this out? How do we figure that out? Well, okay, what do you do? Well, tell me why you're doing it. The whole thing's 360, right? Why are you subtracting 150? Yeah, he's right. Let's see if we can get a little bit more mathematical thought. You're absolutely right. If I call the thing I'm trying to find, the measure of AB, let's call that x. So what else is also x? BC, right? So that means all the way around it's going to be 360. So if I add these two x's together, plus 150, you get the whole distance around, which is 360, which is what you said to do. If I want x, I'm going to subtract 150 and divide by 2. But now I've got the little equation to show it. So 2x equals 360 minus 150. That's a 0. That's a 210. So that means x is 105. Am I doing that right? I'm not good at the adding and subtracting, but I think it's 105. So what's the measure of AB? 105 degrees. So absolutely right. So you're using the fact that we've got some congruent pieces here. Very nice. Okay, let's look at this example. Find the measure of arc CE, arc DE, arc CE. So let's see what's going on here. I have a diameter, and I know that because I see the center and I see this chord going through it. And I also have a perpendicular to it. My theorem says if it's diameter and they're perpendicular, then it must be a perpendicular bisector. So that's going to be congruent, right? So since these arcs are the same, these little pieces here are the same, this piece and this piece will also be the same. So that means that if I could just set 9x equal to 80 minus x, solve for x, I get 10x equals 80. Divide both sides by 10, x is 8. So now what is the measure of arc CD going to be? 9 times x, or 9 times 8. And that's going to be 72 degrees. They are congruent pieces, so what's DE? It's also going to be 72 degrees. And then once the whole thing together, you can add the two pieces together. 144? Yeah. And then I've got another example here. I'm looking at this. Find the measure of segment CU, segment QU, and the radius of the circle. Okay, so I see 16, 16, right? These are congruent pieces. And then I see that I'm taking distance. I know that because I see the right angle markers. Because these are congruent, it must be that they're equidistant. So this piece must equal that piece. So 5x minus 9 has to equal 2x. They're equidistant, same distance. So what do I do? 3x equals 9? Subtract 2x and add the 9. Divide by 3. Looks like x is 3, so what's CU? 2 times 3, that's 6. And then QU, where's QU? That's this piece. Oh, what's QU going to be? Right here?
8.
Why?
If the chord is perpendicular to another chord, then bisects it.
Bisecting, right? Yep, that's what's happening here. So that one's going to be 8. Now the radius, okay. So let's see. It all depends on how you draw the radius. So, I mean, I can continue this and make a radius this way, if I thought that would help me. But I'm seeing a right angle marker here. So I think what I'm going to do is I'm going to draw the radius CR. Because this is a right angle, this piece is 8, CU is 6, 6, 8, 10, right? That's a 3, 4, 5 triangle in disguise. So my radius is 10. And the trick of these is like drawing the right radius. There's, you know, infinite number of ways you can draw these radii. But if you kind of connect those, you can see that nice right triangle, and you can use what we know. Do you have a question, Ross?
For C, number 3,
Huh?
since you have the right angle, or the right angle mark, doesn't that make it 180 degrees?
What big 180 degrees? Yeah, from here to here it is. Well, this will be 180 degrees, and this will be 180 degrees.
Oh, I won't.
It's not a diameter, right? You have to do half the circle to be 180. So since this is not a diameter, it can't be. It has to be less than 180. It is. That makes sense? Just because this is a right angle, the diameter is going this way, not this way. Right? It's going this way, not that way. And it's not on the central angle. Yes. Alrighty. We're up to the U-tries. So basically, that's kind of it. So you've got a couple of pages of U-tries here. Once you work on those for a bit, I'll put the answers up in a minute. I'm going to start putting up answers just so you can start comparing. How you doing? It's okay, you're not quite there yet. I'm just putting up for the record. Let the record show. I'm going to flip, but I'll be back. I'll be back to this page just so you can see what the answers are. Those are the last two. There may be some people up there yet, but it's a while. Look for right triangles. Look for right triangles. That's my pick. I'm going to letter E. Okay. Are there questions so far on just the first 4? How about the first 2? How about that? First 2? Doing well with those? How about third and fourth one? Even good. This is a real good one. I like this one. 6 and 6 red too. That should give you some idea. Let's see what I can put this in. Don't forget your special triangles. So you set these equal, right? 7x minus 8. X equals 2. So 14 minus 8, that's 6. That's 6. This bisects it. 6, 6, 6, right? So don't forget your special triangle.